See, now let's try to build a multi-factor model wherein we are taking the returns on some kind of security or an index as the dependent variable, and we are trying to map them to the various kinds of returns. Probably I'm trying to look at the decomposition of this entire risk into the various risk factors using the historical data, right? So here what I wanted to look at is I have taken a simple example wherein I want to look at the Sensex. Over the last 5 years I have taken the Sensex index values along with the various sector based indexes, around 10 different or 11 different sector based indices on the Bombay Stock Exchange have been taken. All I want to see is, can I map the risk that is inherent, the overall risk that is inherent in the Sensex, can I try to link that with respect to these 11 different sectors? So that is what we are trying to do in the entire process, right? And in this process, we also will encounter that if I am taking these 11 as independent variables, there might very well be a possibility that they are not independent, they are interdependent. So when they are interdependent, what is that I have to do? How do I handle the situation? Now this is what we are going to look at in the whole process, right? Okay. So to do that, initially what I'll try to do is I'll compute the returns for this entire data. So I'll call this new sheet called returns, and probably I'll take the data from the first row as it is, right? I'll copy the first row as it is, and right from this row I'm going to take. So here I'll simply take the second row because I don't have the return as of the first date. So I'll take the return as of the second date, which is from 5th Jan. And if I'm looking at the return, I'll take it as logarithm of the value on the 5th divided by the value on the 4th. Means today's price, today's value divided by yesterday's value. The same thing I'll go across, and I can update it downwards also, which I could clearly see. The same procedure I can update until the last. The same procedure I could have comfortably updated until this particular date. Now for this entire period, I am having the values of the Sensex, and along with that I am also having the various individual indices, individual industry based indices also. Now logically speaking, what is my work now? I want to do a mapping between the Sensex based returns and the returns on the various sectors, right? This is what is the kind of a model. I'm using regression to build a multi-factor model. Because I'm taking multiple independent variables, I'm calling it as a multi-factor model with these 11 different risk factors, right? So with these 11 different risk factors, I am considering, let me try to build a regression model here. After that, we'll discuss something more. Okay, I'm doing a regression. Here, obviously, I require the Sensex as my dependent variable. or let me consider right from here. I'll take Sensex as my dependent and the series of all other variables right from the auto, BankX, etc. All of them will become my independent variables and I have captured even their labels. So my overall expression is coming out like this. It is working out as, my overall expression works out as the return on the Sensex is equal to minus 0.00011 plus 0.115 times the return on auto index, then plus 0.226 times the return on the banking index. So it keeps on going like this, and that is what finally works out as the overall formula for the return on the Sensex. Right? Now, this number is giving me the coefficients. These are the typical estimated betas. If I'm looking at from the model's perspective, the estimated betas with respect to the various elements are going to be these numbers, and corresponding t statistics are going to be this, and corresponding p values, which are indications of the significance, are given out here. Anywhere the p-value is less than 0.05 indicates that that variable is significantly contributing to the model. Otherwise, it is not significantly contributing. So here I could see all these values less than 0.05, which means all of them are, this is less than 0.05, less than 0.05. All the variables except for power, all of them are less than 0.05 and they are contributing significantly to the model. And overall, the R squared that is coming out of this model is also almost 97.62%, which is indicating that the return on the overall Sensex can very well be attributed to the returns that are coming up on the various individual indices. Right? So an OLS, ordinary least squares regression, is what we have performed, wherein I have taken the daily returns of the Sensex, as the dependent variable, and I have regressed it against a whole set of indices. Right? And the t statistics that we have typically got are testing for null hypothesis that the factors, each particular factor's beta is 0 versus the alternate hypothesis that it is not equal to 0. And the p-value less than 0.05 is a clear indicator that the true value of the factor coefficient is not equal to 0. It is either positive or negative. Now, if I keep that aside for a minute, probably these are my betas. Just to go ahead with, these are my betas, right? For a simple security, or for a, for a simple security, now I could clearly see that these are the betas that are existing corresponding to each of the different industry-based indices. So these are the net betas. But at the same time, I also require the variance-covariance matrix. This is what will help me to understand what proportion of the variance of the Sensex is attributable to these various industries and what portion of it is really not attributable. So for that I require the variance covariance matrix, right? We'll try to compute that variance covariance matrix. Now if I go back to the data and I want to compute the variance covariance matrix for all the various factors. I want to look at the variance covariance matrix for all the factors so that I can compute the variance of the Sensex that is attributable to these various factors, right? So that's the reason I will go with the computation of the variance covariance matrix for the Sensex. I mean for the various independent variables. All right, I'll look at the variance covariance matrix. So for that I will take these headings as it is. Here I will consider these headings, and at the same time here also I'll consider the headings in the form of a transpose. Now what I'll typically try doing literally here is I will take the covariance, right? I'll take the covariance between the returns of the auto, comma, the returns of the auto itself. So this is nothing but the variance for BSc auto returns on a daily basis. This is a daily variance, and the same logic probably I can go across and I say that these are the variances across. Variance and the covariance between auto and bank X is around 0.00134. Auto and consumer durables is somewhere 10 to the power of -5. So some such kind of quick calculations I can talk about. Now the same logic I can extend to all the other pairs by simply changing the first the area relating the range relating to the first variable. So let me change all of them alphabetically. So this is G, then let me change this to H. So let me go ahead with all this stuff. Then I have I, then a J, then a K, L, and an M. So for all these 11, I'm looking at their pairwise variances as well as covariances. So this has created the variance covariance matrix for us across all the numbers. These are the daily variance and the covariance numbers. Now what is that we are saying? If I have to really look at, right, if I have to really look at the variance of Sensex attributable to the risk factors. If I have to really look at the variance of the Sensex that is attributable to the risk factors, all I'll have to take is the beta transpose times the variance covariance matrix times the beta. Beta transpose is a 1 by 11 matrix. Variance covariance is 11 by 11 and beta is 11 by 1 kind of a matrix. So I'll do a multiplication, right? Probably initially I'll do the multiplication for the first two elements. For the first two elements where I am looking at M multiplication between the beta transpose, which is the transpose of this is the beta transpose, comma, the variance covariance. This is my variance covariance matrix. So this comes as the first step. Then the variance of the sensex that is attributable to the various factors come out as M mult 1 by 11 kind of a matrix, and this is multiplied by 11 by 1 kind of a matrix. So this gives me that the variance of the sensex that is attributable to these various factors is around 0.0001. Now let me compute here individually the variance of the sensex returns. Directly, if I have to look at the variance of the sensex returns, I am simply computing the variance of this around 0.00109, and out of this the variance attributable to the factors, it is coming out as, I can pull this number from here, which is around 106. So I can very well, and if I'm looking at it on an annual basis, probably I'll multiply this by 245, and even this let me multiply by 245. And if I'm looking at the standard deviation here, right, it is nothing but the square root of the variance around 16.33%, and 16.14% is what is attributable to these factors. So specific variance is simply coming out to the difference between these two, and in the standard deviation front it is around 2.52% on an annual basis. The same thing probably if I'm looking at here, I should get the standard error when I'm multiplying it with the square root of 245. Approximately it is coming out to the similar kind of a number, 2.53%. We have got it as 2.52%. So basically all we are saying is the variance of the sensex, which is attributable to the risk factors. Typically I'm computing it using this, and based on this I'm getting it as the systematic risk. So whatever is the square root of it, it is coming out to be the systematic risk, and the remaining part is typically the specific kind of a risk. And as we have seen in this case, the R squared is very high. So it is the probably what is R squared? R is correlation. R squared is the regression coefficient of determination. In a way, I can call this R squared. Whenever I am looking at R squared, I can call this as the squared correlation between the sensex return on one side and the explained portion of the model. If I look at the explained portion as the predicted value, and I compute the correlation between the sensex return and the explained portion of the model and take the square of it, that is what is going to be the R squared. Now here the R squared value is high, probably extremely high as well. So variability in the entire sensex return, which is unaccounted by the various sectors, is very less. That is one level of analysis that I can do out of this data. But here comes the real problem. The real problem is what I term as multicollinearity. Right? That this is what I term as multicollinearity, especially which I look at as the correlation existing between the independent variables. Whichever variables I am calling them as independent, I am taking them as independent in a regression model, the correlation existing between them. So this is as good as saying, probably if I express something as the correlation matrix again, right, with the same kind of a setup, right, instead of covariance kind of a matrix, let's say I want to look at the correlation matrix, right? Let's say I want to look at the correlation matrix pairwise. So I'll simply say equal to correlation between the C column and the C column again. So if I take the correlation between auto and auto, it's always 1. But if I look at it across, between some of them the correlation is high, very, very high. So let me even change, just like the way I have changed it in case of covariance across. Let me change the stuff in case of correlation also. Right, the alphabets or the column numbers, let me change so that I get pairwise correlation between each of the pairs. There could be many other ways, but probably here, rather than the spreadsheet, our intention is to understand the broader concept. So that's the reason explicitly, though it's taking a little bit of additional time, but I'm just spending it out for you to simplify the process. Instead of 11 variables, if you had taken 4 or 5, it would have been simpler enough, but probably the factor analysis would be more and more effective if I am dealing with more number of variables rather than the less number of variables. You can understand and appreciate the concept very well. Now here if you see, between majority of the groups, the correlations are around 50, 0.5, 0.6, 0.7 kind of numbers with respect to auto. Similarly, with respect to a few other pairs, probably between a few pairs, the correlations could be even more higher, right? Between a few pairs, they could be much more lesser also. Some of the sectors may not be correlated that much, but at least what I could see is there is hardly any kind of negative correlation that is present between any of the sectors, right? At least in majority of the cases, the correlations are positive only. And just to simplify the numbers, probably I would like to round them up. At least from a visual perspective, I would like to look at only 3 digits in terms of the correlation. Okay, so this is the correlation matrix that is there. And probably if I look at the top 5 numbers, just to see which are probably the top 10 items, ignoring the ones, right? So probably instead of 10, I'll look at 20 because the ones anyhow are on the diagonal. Now I could see there is a 0.74. Banking is very heavily correlated with capital goods and power. Capital goods is very heavily correlated with power. So like this, I see metals are very heavily correlated with power. So some indices are very heavily correlated among themselves. So this is what I term as the multicollinearity. Whatever are the independent variables, if I see the correlation between them is very, very high, right? It is difficult to estimate the regression coefficients. If I see this correlation is very, very high, it is very difficult to estimate the regression coefficients effectively. And that situation is what we call as a multicollinearity situation. Two or more independent variables are highly correlated. The efficiency of the estimate, whatever is the estimate that we are giving, the efficiency of the estimate is actually getting reduced. And especially this I could very well see. Let's say I have created a model with three variables and I have got the equation as y equal to a plus b1x plus b2 x2 plus b3 x3. b1, b2, b3 are the coefficients. Now suddenly I add a fourth variable to the data. What could very well happen is the b1x1 plus b2x2 plus b3x3 plus b4x4, whatever we are bringing in, there could be a possibility that b1, b2, b3 change drastically just with the addition of b4. Now that is where the system of multicollinearity will come into picture, which means one additional variable you are bringing to the table, the whole coefficients and the whole model is getting distorted. Now that is what we are calling as multicollinearity, and this is occurring because various independent variables which we are taking to explain the regression, they are really not independent. They have very heavy pairwise correlation that is existing between them. And especially when we are dealing with lots and lots of time series data like this, it's very much possible that the correlation between them could be much higher, which means the factor betas that we have estimated, they cannot be estimated with precision, right? So that's one important point that we have to understand. Right now here, how do I get to the correct one? This is what we'll talk about, the multicollinearity that is present in our results, right? So if I typically see that the correlations between the individuals pairs is much higher, we can very well talk about multicollinearity being present. And if at all this multicollinearity is present, the best way to go about in the estimation of the beta is go with on an individual basis only. Single factor models, right? Go with a single factor model, and probably but no one single factor is going to dominate the entire process. Is able to explain the overall variation in the sensex. So the no single factor model can explain the returns in the sensex to the extent of an R squared of 97 or 98%, which again tells me that I cannot directly rely on a simple single factor model. So there is something that I need to bring into the table, and that is where we talk about orthogonal regression, or this is where we bring in the concept of principal component analysis, wherein, or sometimes we call it as a factor analysis, wherein we transform these independent variables, so-called independent variables, in such a way, right, in such a way that they become completely independent of each other. So anytime we talk about a multicollinearity problem, the best way to solve this multicollinearity problem is applying a principal component analysis to all those variables which we want to treat them as independent variables in our regression. and whatever the components that come out of this principal component analysis, the output of the principal component analysis, we call them as components or factors. Whatever the components or the factors that come out of this principal component analysis, use them as the explanatory or the independent variables now instead of the original 11 variables. Instead of these 11 variables, use the new variables that are getting created using the principal component analysis, right? So that is the way out easier, and to perform principal component analysis rather than a spreadsheet like Excel, we can depend very heavily on some statistical based softwares. Probably I would like to use SPSS in this context so that we can understand it much better. Okay, let me try working out using SPSS. I'll try to import this data into SPSS, and that is where let's try to operate it out, right? Okay, I would like to import this data into SPSS first of all. Let me save this. I'll open an Excel file. Okay, in the here I do have this. Okay, I'll get it from the return sheet, and I'll pick up the data from A1 to, I'll pick up the data from A1 to M column. M1244 is the data that I would like to pick up. All right. So this is my data that I have got from Excel sheet into SPSS. Fine. All right. Now comes here. Conceptually, what is going to happen is this entire factor analysis works on the principle of eigenvalues. So the eigenvalues are typically computed for this matrix, and the collinearity is multicollinearity is simply removed by transforming the existing variables into a different set of components. For that, what I can do is I'll go into analyze. I'll go into this dimension reduction calling as factor analysis, wherein I would include all these so-called independent variables as a part of factor. And here I would look out for KMO and Bartlett test, which talks about the applicability of the factor analysis or the effectiveness of the factor analysis for the model. And I would very much be interested in extracting, let's say, the all, I mean, the because I am working with 11 variables, I am interested in extracting all the 11 factors. I would also look at the correlation matrix and I would get the principal components. And here we use an algorithm called Varimax rotation algorithm, and I'll get the rotated solution as well. And I would like to save the variables. I'll talk about what is that we mean by saving the variables. And I would also go for displaying the factor score coefficient matrix. And using this, what I typically go about is I will run. There are 11 components that we are creating. Okay, now initially you could see that each of the component that got created, here you see KMO Bartlett test, KMO measure of sampling adequacy is 0.943. Anything greater than zero point 0.5 is an indication that the KMO Bartlett KMO test or the factor analysis is sufficient enough. And a significance level of less than 0.05 is indicating the sufficiency of the factor analysis for this particular model. Apart from that, what we are simply seeing is there are 11 factors that got extracted in this particular manner. There are 11 factors that got extracted in this particular manner, wherein I could see that the component 1, whatever it is like it is formed by taking 0.224 times the index, 0.224 times the auto based returns plus 0.313 times the banking returns, bank X returns plus 0.142 times the consumer durable returns plus and so on. This is the first component that got formed. Then the second, then the third, 11 components are formed in this particular manner, right? So these are the 11 components that got formed, which are typically I call them as component 1, component 2 up to component. So the eigenvalues for me, these are the eigenvalues. So the eigenvalues are coming out as 1.15, 1.13, so on. And percentage of the variance that is explained is coming out in this manner. All of them are significantly explaining the variance in the data overall. And the component transformation matrix is actually coming out in this particular manner. Now, what is that we can typically do using this data, right? Now, what is happening is using this rotated component matrix, a new set of, so these are my eigenvectors. The eigenvector is, okay, component 1 is like this, component 2 is like this, component 3 is like this. So this is how the components are typically extracted. If I see in component 1 there is a heavy weightage on capital goods. Component 2 is heavy on consumer durables. Component 3 goes heavy on oil and gas. Like this, these components are typically formed. This is C1, this is T2, this is C3, and so on up to C11. Now what is coming out is using these numbers, right? Using these numbers, now I could see the component score. These are the calculations that are typically being done to arrive at each of the component. Capital goods is having a very high value in the first. Consumer durables is having a very high value in the second. Oil and gas a higher value in the third. So these are the values that are typically being used to compute the new factors. So 11 new factors got found in this particular manner. So what you could see is the correlation now, if you look at between these 11 factors, it's almost zero. 0 between each of the pairs. So they have become now actually independent. Now these factors are really independent. They are not interdependent. Now what is that I could have done? If required, I'll copy these factors, right? I mean, to explain things more better, what I could very well do is I'll copy these 11 factors, whatever got created. Now I will try to run the regression between my sensex returns and these 11 factors. I could do this in SPSS as well. Otherwise, what I'll do is the factors that got created, I'll copy them, right? And here is where I'll create some new columns. Right, here is where I'll create the new columns and I'll try to paste those numbers. Probably let me try to paste them in a general format. And it's better that I increase even the minus 0.28666. Are these the numbers? Yes, so these are the numbers. So probably I'll call them as factor 1, factor 2. For simplicity purpose, I'll try to call them up to factor 11. And I could see that till the last, all these numbers are existing. Correct? All right. Now, if I look at the correlation between, pairwise correlation between these factors, I would really see, just for a sample, I would like to look at the correlation between factor 1 and factor 2. I'll definitely get the correlations between the pairs very, very close to 0. You see, 10 to the power of minus 8, if I round it off, it's as good as a 0. So, which means these factors are completely independent now, right? And now each factor, we know from SPSS the way it got computed. Each factor, it got computed through this particular formula. Each factor got computed now through this particular formula. Now what is that we are simply saying? Now I will do the regression. Right, in Excel or any other tool, I'll do the regression now, wherein I am going to consider the sensex as the dependent variable, returns on sensex as the dependent variable, but from factor 1 to factor 11 is what I call as independent variables. Now they are really independent for me. Correlate, the R squared still is 97.62. Even in the earlier case, the R squared was still 97.62. Even now the R squared is 97.62 itself. But this time the reliability of the coefficients is much, much higher. Now these coefficients are, let's say if I am talking about PC1 or the component 1, which is the factor 1. The coefficient of that, so the formula now will become, now the return for the sensex, the return on the sensex is as good as, I'll write it as 0.000361 plus 0.003362 times the factor 1 plus 0.002118 times the factor 2. It goes like this. right? These are the weightages that are going to come out. And of course, the factor probably all I could see is all the factors are really significant here. The p-values are telling me that all the factors are significant. So these are the coefficients that are going to operate out, which means if I am looking at factor 1, probably it is 0.003362 times. When I am saying factor 1, I know the factor 1 is typically 0.224 times auto. If I have to look at now from an auto perspective, okay, let me copy these components part. Let me copy these components part now. If I look at these components, okay, this is what is the auto part. So the factor 1 is actually having 0.224 times auto, whereas factor 2 is having 0.193 times auto. So logically speaking, if I multiply these with these, this is what is coming out to be the upgraded beta for the auto index. Now if I have to look out for upgraded betas for the each of these indexes, I am simply looking at the matrix multiplication between this and each of these factors. So this says, okay, for the auto it is 0.00828, and the same logic I can very well take it right here. I can again do here, let me do matrix multiplication between these comma these, right? I'm doing a matrix multiplication between these two sets, giving me that this is the coefficient, and across all right, let me again do it. Matrix multiplication between this set comma this set, right? Between these two sets, if I'm doing a matrix multiplication, yes. So these are the coefficients that are actually coming up. So what I could see is now the betas have changed drastically. If I had done the regression in the original way, these were the betas for each one. Let me come back again. These were the betas in each of the cases. But now what I could see is the betas have differed. Now if I had seen now the betas got differed because of this particular equation. The betas have changed across. For some of them they were higher, and in some of them they are lower. So the betas have significantly changed across. Compared to, so this is the way out, right, that I can very much operate out on my coefficient. The betas have changed across, and that's the way out for me to work it out. So again comes out that the variance that is explained by the factors is around 97.62. Unexplained is something else. Now here the message is very clear that this is the way the allocation is happening to each of these sectors across the various stuff. So that's how the factor analysis is in some cases helping us out in terms of improving the removing the multicollinearity among the independent variables, and also helping us in terms of coming out with the better estimates of the coefficients as a part of the regression model, and helping us in terms of determining the variance contribution of the portfolio of the risk factors to the overall dependent variable much more effectively. All right. All right.